Hey guys, how's it going? My name is Greg Hogg and welcome to this beginner tutorial in PyTorch. In this video, I'll show you how to make a CNN or convolutional neural network in PyTorch for fashion MNIST, where the model is going to take in an image of 28 by 28 pixels and it's going to try and predict what article of clothing it is. It could be one of 10 different possible clothing choices, like a t-shirt, a sneaker, a boot, and so on. We're going to make that model, and I'm going to show you how to do that by switching over to Colab. So I'm just going to start with a few imports. We'll get Torch, TorchVision, and TorchVision.transforms. And here we're going to check if we have CUDA available. Firstly, we don't in Colab by default, so later when we do the GPU stuff, I'm going to switch this over to a GPU. And thus we should see that our device is CUDA 0 if Torch is available, otherwise it's CPU, and for now device is going to be CPU. Now here we're going to get a transform, which is going to be the 2 tensor, so we'll convert everything to tensors. We're going to set our batch size to 8, so that means at a time our GPU is going to handle 8 different examples. And our training set is going to be the TorchVision fashion MNIST, where we store that in ./data, and training set is true because that's the training set. We want to download that and we'll automatically run the transform, which is that to tensor. We're going to do that similarly for the test set, except train is going to be false. And these are our list of ordered different classes. So in fashion MNIST, the first index corresponds to a t-shirt / top, second is trousers / pants, and so on. There's 10 different classes there. After you run that, you should see that the data was downloaded accordingly. Now we're going to learn a little bit about the data set. So here we get an iterator. Train iterator is iterating over the train set, and we'll get an image and label pair, which is next on the train iter. So it's going to iterate once over that iterator, and we're going to see that the first image's shape is a 1 by 28 by 28 tensor, and its label is 9, meaning that it's the last index because it's 0 to 9. So the last index is a class of ankle boot. Okay, so when we visualize this in a moment, this image here, we should see that it looks slightly like an ankle boot. Not that much though, because fashion MNIST is pretty ugly. With this line of code here, we're outputting that the minimum of the entire image tensor of all of those pixels in the image, we're going to get the minimum, and same thing for the maximum. The .item function takes a tensor that's just one value and it converts it to an actual Python value. So here we should see that the minimum is 0.0 and the maximum is 1.0. So the pixels in the image are just values between 0 and 1, 0 meaning pure black and 1 meaning pure white. Anywhere in between, it's getting brighter and brighter as it gets closer to 1. Here we're going to visualize the image, so we'll get matplotlib to do that, as well as a little bit of numpy. So we'll get numpy image is just that same image that we got above of the ankle boot, but converting it to numpy, just a slight transformation from the PyTorch tensor to the numpy tensor, and print the classes sub-label. Okay, so classes is our list of classes here, and it's ordered so that it accompanies that index. So here, remember, the index label was 9, and so if you do classes sub 9, that should get the actual name of the class. So hopefully that outputs ankle boot in a moment. And we'll do plt.imshow. That's how you print images to the screen in NumPy. We're going to do a slight reshape because PyTorch tensors by default have the number of channels in the front. Remember, an RGB image has 3 channels, red, green, and blue. And in fashion MNIST, we have just grayscale images. They're just a brightness value, so we don't need 3 channels. We just need the 1. But again, the channels is still technically at the front in PyTorch. So we're going to move that to the back so that matplotlib can print that well. And we're going to run that. We can see it outputs ankle boot because it indexes that class and gives it the label. So the label was 9. It outputs that ankle boot right there. And the plt.imshow is going to show in this kind of funny green-black color where we have our 28 by 28 pixels. And hopefully this looks to you like an ankle boot because it's supposed to be one. If you look in the classes list, you'll actually see their sneakers as well. It's kind of tough to tell which is different, which is part of the reason this model is not going to get precisely perfect, but close enough. If we inspect our training set and test set, we should see that the length of the training set is 60,000 and the test set has 10,000. So we have 60,000 image label pairs in the training set, and we have 10,000 image label pairs that we're going to use to test the model later. we're actually also going to convert the training set and split it a little bit into a training and a validation set. That way we have our training set, which is what we actually train the model on. We'll validate while we're training the model on a validation split. And then at the very end, we'll use the test set to finally assess the model's overall performance. So with this code right here, we can do that. We get train set and val set is the torch utils data random split. So we're random splitting the training set, and we're giving the first partition 50,000 and the second 10,000. So that original 60,000 in the training set, we randomly split it so that the train set is now 50,000. We have this new val set for 10,000, and the test set is going to stay the same. So we should see 50,000 for the train, 10 and 10 for the val and the test. Now remember, our GPU is only going to take in batch size many examples at a time, which we currently have set to 8. So the number of batches in the training set, remember, we're going to split this 50,000 into however many batches of 8 so that the GPU can actually take in those examples. We have 50,000 divided by the batch size, which again is currently 8. So we should see that the number of batches in the training set is 6,250. So as our model is going to be training at taking in those batches of 8, it's going to need to take in 6,250 batches to get over one epoch of the training set. And similarly, we should see that the number of batches in the validation set, also in the test set, should be 10,000, that number there, divided by the batch size. And so it's going to be 1,250 batches make up both the test set and the validation set. Now, if we look at the type of the train set, which should be the same as the val set and test set, it's a data set and also a subset. In PyTorch, we don't generally iterate over data sets. We actually wrap them in a data loader first. So we have train loader is going to be a data loader of the training set. We specify the batch size. So when we iterate over, we're going to get batch size many examples as we go. And for train, we want true and don't really worry about the num workers. Val and test loader are going to be very, very similar. You're just plugging those in, but batch size is going to be the same. You could alter that if you want, but it's easier just to keep it. And for val and test, there's really no need to shuffle because we're just evaluating. Now here's where we create our model. I'm going to build it up in a few different steps. So firstly, some of the structure. We're going to import torch.nn as nn. That's basically our neural network layers. And something very similar but slightly different is the functional as f, which is kind of like layers, except they're not actually layers. They're more so just functions. And this is what we're going to use to apply the ReLU, which you could do as a layer, but we're going to do it as applying a function, just so I can show you both of these techniques. Now, when we're making a neural net, we make it as a class, and then you give it a name. That's whatever you want. I called mine neural net. And in brackets here, you do need nn.module. And one of the two important functions that we're going to have is init self, and it's going to call super.init. We're going to do some other stuff here. And there's also going to be another function that's really important as well that we're going to talk about after. Now in this function, we're going to create the layers that we need. Since this is a convolutional neural network, our first layer is going to be a conv2D. So here, don't worry about this part quite yet. You'll notice we're going to store the layers inside self here, and I'm giving it this name of conv1 because it's our first convolutional layer. Now in this case, it's a neural network.conv2D, a two-dimensional convolution, and it's going to take in channels equals to 1. Because this is our input layer as well, and our input was, well, what tensor do we have there? We saw that our shape of the images was 1 by 28 by 28 images. Okay, so our channel is first here. We have in channels is 1 because this is 1 here, grayscale images, and out channels is however much depth we want to convert it to. So we start out with 1 depth, and I decided to convert this to 256, which means we have 256 filters, and they are going to be 3 by 3 windows. This 3 is implicitly saying 3 by 3 window, and we're going to make a stride of 1 so that it takes our 28 by 28 images, and we're actually going to lose 2 dimensions after this. So after this layer, the image will be converted to 26 by 26 by 1, and we're going to continue our network from there. Now this is far from the end of the network. We'll build this up shortly, but for now I want to show you the other main function, which is how to actually invoke these layers. And it's what we call forward, the forward pass, which is where you take the input and you actually run it through the network to get our output. So if we define forward, which takes 2 important things, it takes self so that we can access those layers, and x, which is basically our batch of images or whatever you happen to be throwing into it. So here in forward, we're basically telling the network what to do. Here in init, we told the network what it has, but here in forward, we're telling it how it actually works. For now, we're just going to run our batch of images through the convolutional layer. And so that is as simple as x, which was previously the batch of images, but now it's our updated tensor. X is equal to the self.conv1, because we have access to that convolutional layer, and we just pass x through that. So this runs x through the convolutional layer. It creates our what will be a 256 by 26 by 26 tensor. We'll see that shortly. And actually, I'm going to print that to show you that that is really the case. If we print x.shape in here, and we'll run this, in a moment, I'll throw a batch of images into our network and show what the shape is. Now, firstly, we have to actually instantiate our network. Because this is just a class, we have to make an object that's an instantiation of the class. So we'll do net, just short for network, is neural net. So calling that class there, you don't have to pass it anything in this case. And net.toDevice, because if you remember from way above, we specified that our device is CUDA if we have a GPU, otherwise it's CPU. And for now it's CPU, but it doesn't really matter. We're just going to move it to that device. And if we run that, that's going to make our network, and it's going to move it to the appropriate device. Now with this code, we're going to go for I and data in enumerate the train loader. So we're going through the train loader, and each time when we enumerate, well, I is just going to be a number, so don't really worry too much about that. But data, it's going to have simultaneously a batch of images and their batch of labels. So data is actually a tuple where it has the first thing is the batch of input tensors, and the second is the batch of labels. And so here we can unpack that with inputs is going to be data sub 0.toDevice. You have to move that tensor to the device where the network is so that we have our inputs and labels tensors. And so print input shape, the inputs.shape. This is going to output what the shape of the images is before it goes through the network. We saw before that it should be 1 by 28 by 28. Here, after the network, so if you do net of inputs.shape, that means we're running the inputs through the network, and then we want to output what the shape is. If we do a break here, that just means we're only going to get one batch from the train loader, and we don't need to see the rest. So if we run that, we get an error that none type object has no attribute shape. The reason for this is because this function always has to return the tensor. Okay, otherwise it's doing stuff, but it's not really remembering what it's doing. So here, if you return x, we run that, and then we run this stuff again. So here we have 3 prints, 2 from here and 1 from up here. So our input shape, this is this print here. The input shape is a batch of 8 images that have 1 channel, and they're 28 by 28 images. Perfect. And then we get this print here, which comes from this. So that means after the network, we're printing that shape there, which is 8 by 256 by 26 by 26, just like we said. And we're actually printing this again, just to really show you that we're accessing the same thing there, which is, again, 8 by 256 by 26 by 26. So that's how we create, instantiate, and actually use a neural network, but we want to create an actual model here, and we have no need to print that shape again, although we will need to print other shapes in there. So now I'm going to carry on forward making the layers of our model. Often accompanying a convolutional layer is a non-learnable, just max pool layer, or possibly an average. This takes 2 by 2 windows, and it's just going to take that window and take the max value of those. Don't really worry if you don't know the specifics here, but that's what it would do. And as we build up the layers, it's probably good to go down here as well and just say that after we're going to do our convolution, we're also going to do our pooling. So x is self.pool1 of x. We're just going to keep building up x. First, it was the batch of images, then it was it after the convolution, and now it's this after the pooling. So as I said earlier, we're going to use f to apply the ReLU nonlinearity function. You could do that in a separate line here, but I'm going to just kind of wrap it around this one so that it applies the convolution, then the ReLU, and then the pool. So we'll do f.ReLU all in lowercase like that. And then just to run all this stuff again to make sure it's working, we run this and this. And we should see that again, after our network, it's now going to lose a lot of it because of that max pool. And it also did the ReLU function. Now you might be wondering how I came up with some of these numbers. You'll see that the 256 is kind of random. It's just a relatively large power of 2. And when I made this by myself, it seemed to work pretty well along with the other stuff we're going to make shortly. A kernel size of 3 by 3 windows is relatively standard, but there's also lots of different stuff to play around with as well. Here I'm going to create more of the network. It's going to be similar to before, just more convolution and pooling. So we'll take in channels equal to 256 because before our out channels was 256 over here. So that's got to be the same number in there. Out channels, I'm just making it a bigger power of 2 up to 512 and the same kernel size of 3 by 3 windows and another max pooling of a 2 by 2 window. I'll do this one more time. And so convolution 3 and pool 3 in channels is now 512. Out channels, I'm going to make another bigger power of 2, make it a smaller kernel size because the 2-dimensional size is actually getting pretty small here. And another max pool 2 by 2, the image is going to be really small. And if we adjust this over here, we can do this just 2 more times. We get x is the ReLU of conv2 of x and then pool 2 of x. We'll do that once more, the ReLU of conv3 of x and pool 3 of x. If we are going to run this, we'll see our shape over here. After the batch goes in, we have 1024 channels because we specified that the last channels here should be 1024. And then after all of our kind of minimizing stuff, we got our max pool 2 by 2 at the end, which finally converts that to just a 2 by 2. So it's basically a 2 by 2 image, really blurry, really small, and then it's super deep. So instead of RGB for 3 channels, it's 1024 channels deep. So that's our tensor after this piece, and we're going to add a little bit more here, but no more convolution stuff because the image face is way too small now. The first thing we're going to do is basically make this image-like thing, this really long, skinny image, into just a super long vector. And we do that by flattening it out. So that's a neural network.flatten layer, and we have to, again, call it down here. So we'll say x is the self.flatten of x. If we run all of this stuff, we should see that our batch of 8 images got forced into a 4096 dimensional vector because it was just 1024, but that was a 2 by 2, so there was 4 1024s, so we stretched that out into this massive vector. And now we can do normal linear layers, like in a fully connected neural network. So to do a standard linear layer, we're going to do self.fc1 for fully connected 1 is a linear where the in features is 4096, that's stretched out vector, and out features is whatever we want. This is just a matrix multiplication, and so we're going to convert that to 1024, just a smaller power of 2. It could have been bigger. I'm just going to make it smaller so that the network is not massive. And here we're going to, as usual, just throw it through that layer. X is now self.fc1 of x. If we run this stuff again, we should see that our output shape, our batch of 8 images, got converted to 1024 dimensional vectors. A useful technique to combat overfitting, which is basically training too hard to the training set, is the idea of dropout. And so we'll add that layer here. We specify the probability is 0.3 or 30%. And what that means is that for each of these 1024 values, we're going to give each of them a 30% chance to drop out or just turn to 0. And it turns out that this is good for overfitting because it allows the model to pick up on many such patterns and not rely on just the same old technique every time. If that didn't make sense, don't worry about it. It just allows overfitting to be a little less of a problem. So as with before, we should be adding this in over here with x is the self.drop1 of x. And actually, we also should be applying some sort of nonlinearity to the linear function with a f.ReLU of the fully connected layer, because this is just linear by default. Now I'm going to add one more of these linear dropout combinations. So we're going to do self.fc2 and drop2. And this in features has got to match this with 1024. We'll keep out features as 1024 just to add in a layer here. And we'll keep the dropout at 0.3. And as with before, we have to add this to our forward function. So we'll do x is the f.ReLU of self.fc2 of x, and then we'll add in the drop2 of x. And then finally, we have to add in an output layer, where this is going to be another linear layer, but we don't want any dropout, and it needs to end in 10 values, because we want this to end in the probability distribution over the 10 classes. So this has got to end in 10 values. Luckily, this is pretty easy, and so we're just going to add self.out for the output layer. It's another linear layer where the in features is going to be 1024 and out features is forced to 10, because again, we have 10 different classes, 10 different types of materials. And now we've just got to finish off our forward function. So we'll do x is equal to self.out of x. We're going to run this, run these two again. And we should see that after our network, our batch of 8 images, which were 1 by 28 by 28 images, have now been converted to a batch of 8 10-dimensional vectors, where each of those 10 values is basically the probability distribution over the classes. Now, the reason it's not exactly the probability distribution is because here we haven't specified that there's an activation function here. The activation is just linear, which means each of the 10 values are actually numbers anywhere from -infinity to infinity. If you wanted our network to exactly model the probability distribution, you would have to end this in a softmax, but we don't really need this because of how we're going to use our loss function. Now, something useful but not necessary to know is how many different parameters or learnable numbers we have in the model. And so here we can count them up with, we'll start numparams as 0. We're going to iterate through the network's parameters. The parameters are going to be many different tensors, which are storing numbers. So we're going to flatten each of those tensors, and then we're going to get the number of things that are in it. And the number of parameters is going to go up by each of those tensors. If that didn't make perfect sense, don't worry, I'm just counting up the parameters. And we should see that the number of parameters in this model, we are learning 8,536,074 different numbers in our model. Not super big, but still relatively large. Now here we're going to specify a couple important hyperparameters. So we're going to get the optimizer and the loss function figured out here. So firstly, we import torch.optim as optim. That is just the optimizer library. Our criterion or our loss function is the cross entropy loss. So this is the one that it's assuming if you don't end in that softmax. And so we're going to use that one. And our optimizer is the atom optimizer with passing it our parameters. And we're specify that the learning rate is this learning rate here. You can change this, but I did figure it out for our model that this is a good one to use. You could optionally play around with that and see how it affects the training. And note here that we are passing the parameters of the model to the optimizer. So that's a little bit different than it is in TensorFlow, and we're going to see how that fits in shortly. Now here's where we define the training loop, which is a lot different than it is in TensorFlow. In PyTorch, you have a lot of customization, and you basically write the training loop all by yourself. Now, because of that, there's going to be a little bit more code than there would be in TensorFlow, but since you write it yourself, it's really, really explicit on what you're going to do and how you want to format the output, and it's really nice if you can sacrifice that extra bit of coding. And I think it also lets you really appreciate and force yourself to understand what the training loop is. In TensorFlow for beginners, it's kind of easy just to look at metrics and understand a little bit, but here you're going to have to really understand exactly what the training loop consists of. Here is our training loop, and we haven't written these functions just yet. We're going to do that in a moment. So we have 10 epochs, where an epoch is a run through the training set. It's a run through those 6,250 batches of 8 images. That's what forms the training set. We're going to go over it 10 different times, or 10 different epochs. So for epoch index in the range of the num epochs, just means we're looping over that many times, and we're keeping the index. We'll print what epoch it is, and then we're going to train for an epoch. We're going to train the model on each of those 6,250 batches of 8 images. Each time we see a batch, we're going to update the model. And then at the end of all of that, we're going to evaluate the model's performance for that epoch and keep track of how it's doing on new data, okay? Because the training accuracy and metrics are somewhat useful, but really we want to see how the model is performing on new data that it's not using to train. If that didn't make perfect sense, don't worry, we're going to create these two functions and then it's going to fall into place. So let's create the function where we train for one epoch, and I'm going to let that take up the entire screen here. This is a big function, so we're going to build it up a few steps at a time. Firstly, our net, which is the model we created above, we're going to set it to training mode. So we give that true, meaning it's in training mode right now. It could also be in evaluation mode, which we're going to turn it to later for the validation stuff. Then there's these two numbers that are going to be metrics, which we're going to build up over time. The running, which is like it's accumulating, it's running. Loss is 0.0, and the running accuracy is 0.0 for now as well. Those will accumulate. Now we're going to iterate over our trained data loader. And so for each time we do that, we're going to get a batch of data. So we do for batch index, that's just an index, and for data, or a batch of data, which is going to store the batch of images and the batch of labels, we're doing that from enumerating over the train loader. Then as before, we need inputs and labels. This is our batch of images. This is our batch of labels. This is the first part of data, which we're going to move to our device. And this is the second part, which we're going to move to our device as well. So we have images and labels. Neural networks learn through backpropagation, which looks at the model's parameters gradient or its derivatives with respect to the loss function. If you don't know too much about that, I wouldn't worry too much about it. But here, it's important because we have to do optimizer.zeroGrad, which means if you have any sort of non-zero values for the gradients, just set them all to 0 so that when you calculate them properly in a moment, they're properly reset. So this just means reset the gradients, and if you didn't understand any of that, just take it as a required step. Now we get the outputs of the model, which is going to be running the inputs through our network. We already did that above. And what that's going to do is get our shape of batch size, because remember our inputs here, that is a batch of images. So we get batch size by 10. And it's 10 because for each of those images, our model is going to output 10 things. Now we have to talk about what those 10 things are. As we saw above, this just ends in a linear layer where it's 10 different values. Technically, these values could be anywhere from -infinity to infinity. And the reason we chose 10 values is because we have 10 different classes or 10 different articles of clothing. If we go up here, we should see that we have these 10 classes. The 0 index corresponds to t-shirt, the 1st index corresponds to trousers, all the way up to the 9th index or the 10th thing, which is an ankle boot. This same order is the exact same order that is preserved by our network here. And so let me give you an example. Say for one image, our model outputted this. Technically, they should be floating point decimals, but I'll just use integers so it's easier. If we look at the highest of these values, we should see a 7. And we look at the index which that is. Since we know this is the 9th or last spot, this must be the 8 index. And the 8 index corresponds to what class? It corresponds to this one, a bag. So I looked at the highest value because it turns out that the highest value for the vector means that the model thinks that that image is that class. So of the vector that it produces, we look at the highest value, and then we look at the index slot of that. That means that the model thinks that that particular image is represented by the index from that class, which in this case is bag. Again, if that didn't make too much sense, don't worry about it, and we will just continue making our model. So here we have our outputs is net of the inputs. We put the batch of images through the model, and for each of our 8 images, we're going to create those 10-dimensional vectors for those images. For any image that our model receives as input, our model's prediction can either be right, as in its prediction matched the actual label, or our model can be wrong, as in it predicted something that the image was not labeled as. Remember that our batch of images comes with a batch of labels. This is our ground truth answer for what each of those inputs are. And this is just a vector of 8 things because it's 8 labels for the 8 images. Here we can calculate that the number of correct predictions our model got for the batch is the torch.sum, where the labels is equal to the model's prediction for those images. So here we get the argmax of the outputs across dimension 1. Don't worry if you don't know that off by heart, that's okay. But this is a vector of predictions that is going to line up 1-to-1 with the labels of the images, and where the prediction matches the label, well, it got that one correct, hence they're equal. But if it got it wrong, the label of the prediction is not going to match the label of the image, and so that would be wrong. So we sum up the ones where it did get it right, and then we take the item which says turn that into a Python number. This is some integer where it's between 0 and 8 of how many images the model got right for that batch. Now we're going to start accumulating our running accuracy by getting the number of correct divided by the batch size. That itself is an accuracy for the batch, and this running accuracy, we're going to divide it later by the number of batches, so that's an overall average of accuracies across the batches. I know that's a little bit confusing, but we'll worry about the details later. Now here's where we actually train the model. We zeroed out the gradients, preparing it for training, and then we got the outputs of the model for that batch. Now what we have to do is these 3 lines, which is the loss value, it's just one number, is the criterion. We already specified above that the loss function is the cross entropy function, where it compares the values of the outputs to the labels. The labels is the ground truth, the outputs is our predictions. It compares those things and it gets some average loss for the batch. Then we're going to do a loss.backward, which means we're going to go through that loss tensor that was created. It knows how it was made, and it's going to go all the way back through the model's parameters, and it's going to calculate their gradients. now that it knows its gradients with respect to the loss function, well, that's actually what we're using in backpropagation to make the model better. And so the optimizer does a step. And since the optimizer has the model's parameters, you actually pass them in there, it takes this super small step size in the direction of the gradients that it calculated in order to slightly make the model a little bit better, to hopefully make the loss a little bit less on the next batch that it receives. We are also going to add in the running loss plus equals the loss.item. So whatever that loss was, we're going to keep track of that for the batch and add it to this outside running loss value, similar to the running accuracy. Here's where we're going to print some of our metrics, since we've actually done a step in the right direction already. To keep track of what our model's doing each batch, we're going to throw this in, where actually it's not every single batch. Our model is going to look at every 500 batches. So we're going to print this every 500 batches. Otherwise, it would just be way too much printing. Now, what we have to do is we get the average loss across the batches, which is our running loss that was accumulating every time we saw a batch, we got the loss, and we divide that by 500 because we're printing every 500 batches. And so we want to make this the average loss across the 500 batches. Very similarly, we have the average accuracy across the batches is going to be that running accuracy value divided by 500 because we're printing every 500 batches. And for printing, we're going to multiply by 100 so that it's not a fraction. And then it's very important that we set our running loss and accuracy back to 0 because we're printing every 500 batches. And so if you didn't set it back to 0, it would eventually get higher than 100%. And so you need to set that back to 0. Alas, we are finally done making this train1 epoch function just at the same indentation of the outside here. So as in after the loop, I want us to have just a simple print nothing, which is just going to make a new line. So we're going to run that. That just creates that function. And now we'll make a very, very similar validate1 epoch function. Now above our training loop and below the function we just created, I'm going to paste in our validate1 epoch function. And it's all pasted in because I'm going to explain it one step of the way, but it's very similar to the previous one. So first we set the net.train to false, as in this now is in evaluation mode. Running loss and running accuracy are still 0, and we're going to iterate through the validation loader. We get our images and labels batches. Now we have to add in this with.torch nograd, which says in this indentation here, don't worry about calculating gradients. We're not going to need these things because we're only using those to train the model. But here we're not training the model, we're just evaluating it on the validation set. So don't worry about that. We're still going to get our outputs, which is running the image batch through the network. And we're going to get our number of correct is the same thing as before, the same method. Same with our running accuracy, same with our loss, and same with our running loss. Just note that we don't do any of that optimizer.step or zero out the gradient stuff. We're just calculating the metrics. Now here, I actually have to get rid of this because that's really not necessary at all. I don't know why that's there. And then we have to do average loss across batches is the running loss divided by the length of the valve loader. Now the length of the valve loader, you might not know what that is. Well, we actually already calculated that earlier, which was the number of batches in the validation set. I could pass that 1250 or I could pass that 10,000 divided by batch size, but the length of the valve loader, well, think about it. We're iterating over the validation loader, as in every time we take a chunk out of the validation loader, we're taking out a batch. And so how many batches do we have? Well, that's going to be the length of the valve loader, or 1250 right there. Okay, so we need that because in our validate1 epoch function here, we have the average loss across all the batches. Okay, we're not printing every 500 batches now, we're just printing this once. And so we get our whole running loss divided by the length of the valve loader, or how many batches that we had. This is the average loss across the batches, or very similarly, the average accuracy across the batches, and then we multiply it by 100. We're going to print that down there, and we're going to create our function there. Now again in our training loop, we have 10 epochs. So each time we're going to train one epoch, and we're going to validate for one epoch. Every time we train, we saw that every 500 batches, we're going to report our information, our metrics, on the training set for those 500 batches that it just saw. We were taking averages across the 500 batches. And then after we do that, after we get through all the batches in the training set and we report those, we talk to the validation set and we just go through all the batches and then we just report once and say, this is your average accuracy across all of the batches. If we run this, well, it's going to be really slow with the CPU. So I'm going to stop this and then I'm going to do runtime change to a GPU. And then we're going to run all. Okay, here you go. It started. Epoch 1, we have across batch 500, across the recent 500 batches, we have a loss of 1.209, which isn't that meaningful. We'll just look at how it goes up or down. And then the accuracy across those 500 batches was 54.2%. And then for the next 500, the loss was a lot lower. And the accuracy across those batches, the average accuracy across those batches, same with the average loss across those batches, it was 71.6%. It's going up, and every time we're seeing that the average loss in accuracy across those batches is the loss is going down, the accuracy is going up. But what we are most concerned with is what the validation set has to say, which is the validation loss after it did all this training is at 0.404, which is even lower than the training set was, and the validation accuracy is 84.8%. This will continue to go up, or the loss will continue to go down, and eventually you will have a trained model. Okay, I'm stopping the video there, but you'll note that I haven't done anything with the test voter yet. What I want you guys to do as a challenge is get the accuracy of the model overall on the test set. That's how you really prove that this model is good. So let the model train out for however many epochs that you want, and then figure out how you can adjust the above code to test the model on the test set. The Colab notebook is in the description if you want to take a look. I really hope this video was helpful. If it was, make sure to like and subscribe. I will definitely be continuing this PyTorch series, so stay tuned for that. And have a great day, guys. I will see you later. Bye-bye.